Dear viewers, dear shapes enthusiasts, my name is Binz and welcome to part 16 in the BUTTMAM series. Over the course of the series, we've spoken about how this factory selects a number of candidate pieces each time, and then it tries to see if it can assemble the final shape with them. In video 8, I showed you the method that I used to cycle through various candidates based on a pulsing mechanism. And while in that video, I used a manual switch button to simulate those pulses. Obviously, the factory itself doesn't require having to press a button every time you want it to try a new candidate, right? So today I'd like to have a look at this pulsing automation with you. Now, in and of itself, creating a pulsator or oscillator, or whatever you want to call it, is not that hard. There are even several methods to create such things, but the easiest one to comprehend, in my opinion, is just creating a closed loop with transistors and one NOT gate. Let me show you what I mean. Let's find an empty spot on the map, somewhere right here. So what I'm going to do is I'm going to place down a transistor. And then, very simply, the amount of transistors you place down is going to determine how fast your intermittent signal is going to be. So let's place down 5, 10. Let's make it 40 in total. Okay, so 20 here, and then 20 there. Okay, so that's 40. We connect them all with a constant 1 signal, like so. There we go. We connect this up, and then we still need one NOT gate. So now we have a 40 tick pulse. I'm going to remove this one so it gets back to 39. And by placing the NOT gate, we get back to 40. And if now I connect this up, we got a 40 tick pulse or oscillator module. Right, there it goes. I'm gonna place a display for clarity purposes. There we go. That's our intermittent signal. And now the only thing you need to do to speed up this signal is, to speed up the frequency, is remove a certain amount of transistors from this. And if we want to slow down the frequency, well, then we add transistors to it. We make the loop bigger so that the signal takes a longer time to make it around that bend and get back. That's how we can influence the speed of that frequency. So not only is this a way of creating a pulsating device, but it is also the one I started off with. And the first consideration I needed to make was, how fast should I make it? What should the frequency be? Because if I made the pulses too fast, well, then the machine would trip over itself. It wouldn't get the time it needed to process the signals, and it would tilt. But if I made them too slow, put the pulse intervals too far apart, well, then that's just a wasted opportunity, right? It would take the machine forever to find the correct shape, and way longer than was necessary. I did want this factory to be a little more than just a proof of concept. It had to be able to find all of the shapes within what I considered a reasonable amount of time as well. So that consideration, the pulsing frequency, that was the first thing. But then I also started observing something else. Not every set of candidates is created equal. Not every set of candidates took the factory equally long to find. I noticed that there were considerable discrepancies there. Some candidates got lined up immediately, while other times the process would take up to maybe half a second or even over a full second to line up a specific set of candidates. And, well, when you consider the algorithm and the structure of the setup, then that also kind of makes sense. Let's have a look. So here is the machine. So the pulses, they are generated and sent out on the right-hand side, and they travel leftwards. Okay, so when a pulse is sent, then the first machine that pulse will reach will be the duo float cycler number 3. And this duo float cycler, it will need to cycle through all of its candidates. It will need to exhaust all of its candidates before a pulse coming from the right-hand side would reach the second duo float analyzer or duo float cycler. And it, in turn, also needs to go through all of its candidates before a pulse could reach the third duo float cycler, the cycler number 1, and so on and so forth. And you know, because I use logic gates and transistors and whatnot to make all of that happen, then even if, let's say, the rightmost 5 cyclers are all empty, then still a pulse coming from the right would take a longer time to reach the quad float cycler on the left, for example, than it would to reach this module right here. And in the opposite direction, so speaking from left to right, well, every new pulse is going to influence which floating pieces the cyclers select. And whenever any of the cyclers does that, that new piece, that new selected candidate piece is going to affect which candidates the other cyclers will get to choose from in the first place, and therefore the other cyclers located more towards the right of where the pulse just hit, they will also need to reset at that point. So the more leftwards this pulse hits, you know, the longer it will take the finalized output to reach the lane sorter and the validator on the right again. And moreover, not every signal will take the same path. Not every signal will need to travel through the same amount of modules. Therefore, not every piece accumulates the same amount of ticks, and thus the delay for every candidate and every set of candidates is different. And now, given that situation, I felt obligated to match the speed of my pulsating module, to, you know, the weakest link, so to speak. So the shape candidates that took the longest to travel from A to Z, you know, that would determine the frequency of my pulsating module, right? Unless, that is, I could find a way to make a variable adaptive pulse rate instead of a constant one. Aha! Let's have a look. So, we are going to zoom out, and what I'm actually going to do is I'm going to create a manual shape, and I'm going to take a very easy shape. One that doesn't have, this shape does not have any floating quadrants in it, and therefore the fast lane module that we spoke about in video 11, it immediately captured that. But now what I'm going to do is I'm going to disconnect the fast lane module. There we go, that's that. The next thing I need to do is I'm going to force my pulsating mechanism to keep on going even if it found the correct shape, so that we have something to look at, something that I can demo. And then the last thing I'm going to do is I'm going to disconnect the anti-jank device. There we go. So now, if I'm correct, yeah, so even though this is a very simple shape, you know, I forced this pulsating mechanism so that it cycles through all of the candidates, right? You can see this happen right here. So I'm going to go to the cycler 2.3. And we're going to have a look at this wire. This wire is the pulsating wire. So what we are going to do is we're going to backtrack to where it originates, okay? Let's follow it around. Let's follow it to the right. That's where it comes from. And now downwards. Here we are. So here is where the pulse is sent out. This little thing right here. It's a 40 tick module. And what it does is it takes this pulse right here. As a matter of fact, I'm going to make this signal. I'm going to make this signal constant. And in the meantime, if you happen to hear any planes fly over, I don't know if the microphone will catch that. Yeah, I don't know what kind of planes those are, but whatever. So back to the game. This is a 40 tick module, and whenever a pulse comes from the right here, it will move here. And the first thing it will do is it will move immediately into this XOR gate. And as you know, an XOR gate will output a 1 if it receives a signal from either the left or the right, but it will output a 0 if it receives two signals of the same. So 2 1s or 2 0s, then it will output a 0. That's what the XOR gate does. So what I did is when this signal comes in, it will be redirected to the right-hand side of the XOR gate immediately. And this will, you know, trigger a 1 on this wire. And then the same signal travels through a total of 40 transistors. So that's a 40 tick delay. It travels up here, and when that 1 reaches this XOR gate, then the signal will swap to 0 again. Right, and that is how I create this pulsating system. Let's put a set up a display. Now, what this module is good for, as we will see later, is that the pulses are sometimes they are very short bursts of 1s. You see, this may vary, and the reason for that is because not all shapes, not all candidate sets require the same amount. The same amount of time to be found. So this line right here, it is very unstable. Let's call it unstable. And what this module does is it's going to kind of equalize. It's going to equalize that signal, so that when we look at the display, you will see that the intervals between the different pulses may vary, but the pulses themselves will be reliably long, kind of. Right? Let's keep an eye on this for a second. Okay, so you see that happening. The problem with this setup, and I don't know if that's the case for any kind of TMAM setup that you can do, but I noticed that these pulses, you know, they twitch just like right here. These modules, when they switch candidates, the values on these wires, they may rapidly change, right? So we might get a very fast intermittent 1-0 pulse from time to time on this wire. And if that happens, then the cycler modules are going to trip up. So the purpose of this thing is to equalize the pulses a bit. And then at the very end of this line, I swapped the signal so that actually 1 is a default and 0 would be the pulse, right? So actually, instead of a pulse, you could say an interruption on the signal. That's basically the same thing, right? The reason for that is because I noticed that my machines worked more reliably if it had a 1 signal more constantly than it did a 0. So in fact, you know, 1 is the default and then the 0 will serve as an interruption rather than the other way around where 0 is a default and 1 provides the pulse, if you know what I'm saying. Okay, so the next thing I wanted to do was take a look with you at where this pulse comes from. And now we are going to get to the variable bit. Right, so let's follow this line backwards. It originates here. There we go. This is where it comes from. And this module looks more impressive than what it actually is. In the previous video about the lane lister, I spoke about how 16 wires come together right here, right? This is like the crossroads where all of the output signals of all my modules meet up. And what I do is I take a copy of all of these 16 wires, and essentially these 16 lanes are, let's call it delay modules. So I talked about the constant signal with the pulsator and the variable signal with the pulsator. And the way I created the variable signal is by not taking a constant, amount of time to generate the pulses, but to attach the pulses based on the output. So that way I wouldn't have to concern myself with how long the machine actually takes to line up every candidate. I didn't need to make that kind of analysis. What I did was I'm going to decide that all of my output signals have to stay constant for a minimum period of time. And that period of time, if I believe, is also 40 ticks. And if that applies to all of the lanes, then only then will a new pulse be sent out. So these 16 lines right here, they are pretty much identical. I run the outputs into those lines. And this also holds true for the lines that don't have any signals on them. Because as the machine cycles through the candidates, the lines that have signals on them and the lines that don't, they may switch, they may change, right? So you see that sometimes some of these lines light up, which means that they have values on them, and then they will turn off again, right? This is the nature of how this machine works. It tries different candidates, it tries different combinations of candidates, and that will translate into different combinations of wires being used here. Different combinations of wires carrying signals and other ones being empty. So for this module, I want to take all the signals into consideration. Even if they don't have a signal, they need to have that lack of signal for a minimum period of time. And now I would like to refer back to what I spoke about in video, I believe number 3, where I said, video number 5, where I spoke to you about how a 0 is different from a null signal. So when you work with the comparing unit, and I want my comparing unit to catch a null signal, I need to transform it into a 0 first, because a 0 counts as a value, whereas a null doesn't count as a value. So, and then the actual delay module right here is actually very simple. So I transform it into a 0 first, and then I run a copy of the wire all the way up without interruptions. And a twin version I send through, I believe it's a total of 40 ticks, right? So 1 tick, 2 ticks, 3 ticks, 4 ticks, 5 ticks, and so on. And this signal will only carry on. So the signal on the right will be a lot slower than the signal on the left. And at the end of the line, this signal, whether it be a 0 or something else, you know, like this, you can see it happening right here. You know, it takes a longer time for the right-hand side to reach the final comparing unit than it does for the left. And now, all of these 16 lines I connected with AND gates. And that means that only if all of the 16 lines remain constant for a minimum of 16 ticks simultaneously, then we will get a 1 on this wire, and otherwise we won't. That's how that pulsating mechanism works. That's how the pulsating mechanism based on the output works. And that cycles, obviously, because each pulse is going to affect the output. So the signal travels through the entire machine. The pulse is going to do something. And as long as stuff is happening, well, these lines will flicker, right? They will have intermittent or variable or changing values, signals, whatever. And as long as that's the case, this line will output a 1 and no new pulse will be sent through the machine. So basically, as long as we have variation here, it means the machine is still working and no pulse should be sent out. That's the reasoning behind that, and this is how that works in practice. Now I have a similar delay module here. In hindsight, I don't really know if I need it still. But as I said, you know, this was a trial and error process. I think I built this. I might have built this before I built this. And, you know, if it doesn't hinder the process, then I decided to leave it in just in case. And this is how the machine works now. So this is how these pulses are generated. So this again is also a delay module. Then the signal carries on to the part we looked at before. A similar delay module designed to like equalize the pulses. Let's get rid of this again. Turn it into what it was. There we go. And now let's follow this line again. Wait, this is not the correct line, is it? Oh yeah, it is. There we go. Let's follow it to the first cycler. So this is the cycler 2.3. So, and the pulse will feed in here, and here it will start rotating, making this cycler, you know, go through all of its candidates like we've seen in previous videos. And at the end of the line, this is also maybe an interesting fact to quickly talk about. Whenever a pulse comes in, I blocked the output line. Because I noticed that sometimes a pulse would be sent here, it would trick, or it would make this machine switch to a new candidate, and then for some reason that is still beyond my comprehension, another pulse would be sent out prior to that being adequate. So it sent one out even though it shouldn't, and this is why I blocked this signal with this transistor and with this NOT gate. So only if we don't have a signal, then that signal may pass on to the next machine. And while we are at this topic of delay modules, intentional delay modules, let's have a look at some other intentional delay modules which are very similar in setup, but that don't necessarily or directly have to do with this pulsating mechanism. So for example, we have one here. This is between any cycler and its twin cycler. So the thing is, if we select a new candidate, then it's going to take some time for this machine to receive its candidates. And in that time, I am shutting off and repowering the machine, and that is what this line does. So if we can actually demonstrate it live, I think. Let's wait until we get a signal here. So as soon as we do, if I cut this line right here, that is a reset module for the entire machine. So let's wait until we get a signal. There we go. Okay, so if I cut this line, the signal is going to stay, it's going to stay constant, I believe. No, sorry. If I cut this line, if I briefly cut this line, then, the machine is going to be reset. Anyway, doesn't really matter. So, come on. Thank you. So that is one miniature delay module I have right here. I have a bigger one right here, which does the same thing. So if we get a change of candidates in any of the cyclers at the bottom, then these lines are going to be influenced. They are smaller delay modules, but they're also going to only output the signal if the signal stays constant for at least 5 ticks, right? On all of the wires. And this line is connected to itself again. So this basically means, since this line triggers a reset module, it very simply means that if we change these wires, if the values on these wires change, then the module is going to reset itself and it's going to start at the first candidate again. That's how that works. So you can see that a lot of thought has gone into this machine. Working with these pulses, I'm not going to lie, I found it very confusing. It was a trial and error process. In a lot of cases, I eyeballed it. It can definitely be optimized. I am the first person to admit. But since everything is connected to everything else, this becomes a cluster F word of a situation very, very quickly. But anyway, that is how that basically works with the pulse generator. So in a way, I am kind of proud of myself that I came up with this variable pulsing unit, which in turn makes the machine faster than it would be with a constant pulsing signal. So, having said that, I think that's everything I have to say about that topic. So once again, I want to thank you very much for watching. The final thing I'm going to do before I leave you is I'm going to reconnect the wires the way they were. If I can still find where I cut them. Let's have a look. There is one. Oh yeah, and the fast lane module, let's reconnect that. There we go, boom. And then finally, I cut the wires from the anti-jank device. There we go. And the machine is back to normal. So, yeah, thank you very much for watching. I hope you enjoyed. I hope you are looking forward to part 17. We are almost at the end of our journey, still a few videos to go. And I hope to invite you. I hope to be able to welcome you there. I hope to see you then and there. Thank you again for watching. Have a lovely day. I am signing out. Take care. Bye-bye.